Hello everyone, and welcome to our video for section 1.2 of our textbook looking at limits. This is going to be the first of two videos looking at limits. This one here is going to be covering some of the techniques we looked at last year, as well as looking at the definition. So our lesson objectives for this particular video. Number one, estimate a limit using numerical and graphical approaches. Number two, we want to be able to identify ways the limit does not exist. And number three, we want to look at, and we're going to study the formal definition of a limit, often called the epsilon delta definition. Now let's take a look at what exactly a limit is. A limit of a function f of x as x approaches c is the one number the function's values get nearer to as x gets closer and closer to c, but not equal to c. Let me say that again. A limit of a function f of x as x approaches c is the one number the function's values get nearer as x gets closer and closer to c, but not equal to c. So really what the limit is describing is the function's behavior. It is what you're going to do when you're analyzing a limit graphically. You have to go through and approach the number c, whatever x is getting closer to. You got to approach that number from the left and from the right and determine what's happening to that limit. So in order for the limit to exist, as I use values as I approach c from the left, so I'm using values of x that are smaller than c, I know I'm going to be on this portion of the graph here. And as my x values move closer and closer to c, my function values are going to be getting closer and closer to whatever L is. If I come from the right, in other words, I'm going to use x values to the right of c, so x values that are bigger than c, I'm going to be on this portion of the graph up here. And as I move along here, as I move to take x values closer and closer to c, my function values are also moving closer and closer to that same number L. So for this particular problem, I could sit there and say that the limit here, as x approaches c of f of x, is equal to L, because it is the one number my function values are getting closer to as x gets closer and closer to, but not equal to c. You've got to keep both of these pieces in mind. The one number and when x is closer to c, but not equal to it. Let's take a look at an example problem here in terms of identifying a limit based on the function that we have. So in this case, what I know is I'm going to let f of x equal x squared minus 4x minus 12 over x minus 6. And what I want to do is I want to find the limit as x approaches 6 of my function. So what I'm going to do is one of the things you're going to end up doing when you're working on these, and you're going to see an example of it here, is you're going to set up a table. You're going to use x values that are just smaller than 6. So we want to that are going to be just smaller than 6. So in this case, I'm going to use 5.9, 5.99, 5.999. And moving closer as I go in this direction, I'm getting closer to 6. To the right, I'm going to use numbers that are just a little bit bigger than 6. And I want to, as I move closer to 6, I want to be getting closer. As I move closer to the value 6 here, these numbers should be getting closer to 6 as well. So I'm going to use 6.1, 6.01, 6.001. That's a very common pattern in terms of how you choose these values to help you determine what that limit is. So what we're going to do is we're going to plug the values in to this particular function, we'll start out with the ones to the left. So in this case, the first thing I'll do is I'll plug 5.9 in for x. So you can either do it in your calculator, well, you're going to need to do it in your calculator. You can put 5.9 in for x, so I put 5.9 squared minus 4 times 5.9 minus 12 divided by 5.9 minus 6. And when I plug that into the calculator, I end up getting 7.9. I do the same thing with 5.99, and when I do that, I get 7.99. And then when I put 5.999, you guessed it, I'm going to get 7.999 on this particular problem. So I look at that, and I can clearly see that as I move closer and closer to 6, my function values seem to be getting closer and closer to a specific number. In this case, it really looks like, in this case, that as I move closer and closer to 6, the limit here, as x approaches 6 from the left, that little minus sign is from the left, of f of x, that appears to be equal to 8. As I come from the left, approach 6, my function values seem to be getting closer and closer to 8. Now, let's take a look at what happens when I come from the right. When I put 6.1 in for x, I get into that function, so I have 6.1 squared minus 4 times 6.1 minus 12 divided by 6.1 minus 6. I actually come up with 8.1. When I put 6.01 in for x, I get 8.01. And when I put 6.001 in for x, I get 8.001. So again, as I'm looking at this, as my x values here approach 6 from the right, my function values are getting closer and closer to something. In this case, I can say that the limit here, when I look at that, the limit as x approaches 6 from the right of f of x, that is equal to 8. Well, in this case, since I am approaching the same value from the left and from the right, remember the limit is the one number that f of x is getting closer to as x gets closer and closer to c, but not equal to c. So in this case, as x gets closer and closer to 6, I know that one number is 8, and so what I can say on this problem is that the limit as x approaches 6 of x squared minus 4x minus 12 all over x minus 6 is equal to 8. Let's take a look at another example. In this case, we have a piecewise function. F of x is going to equal 4 when x does not equal 3, and it's equal to negative 1 when x is equal to 3. What you see here is a graph of that particular function. We can see that when this here is 3, when x is 3, we get this point down there. Otherwise, we get this graph here. And so, we want to find out what is the limit here as x approaches 3 of f of x. Well, remember in this case that what happens is we've got to we want to find the one number that x gets closer to, that f of x gets closer to, sorry, as x approaches 3 but is not equal to 3. See the difference? See the key? So in this case, as I approach 3 from the left, so I'm over here, as I approach 3 from the left, but not equal to 3, my function values are going to be 4. So I can say, in this case, that the limit as x approaches 3 from the left of f of x, that is equal to 4. Now let's take a look at what happens as I come from the right. As I come from the right, so I'm over here, numbers bigger than 3. As I approach 3 from the right, my function values are right up here. It's still equal to 4. So I know that the limit as x approaches 3 from the right of f of x in this case is also equal to 4. So in this problem, remember the one number that f of x gets closer to as x moves closer and closer to 3 but not equal to 3 is what our limit is. So in this case, I know that the limit as x approaches 3 of f of x is equal to 4. One of the traps, beware of the trap of going through and thinking that the limit is going to be always equal to whatever happens when you plug that number into the function. Okay? It is the behavior of the function as x gets closer and closer to c, but not equal to c. Here are a couple other examples for you to take a look at. I want you to determine the limits here. So what you're going to want to do now, take a look at these graphs. You want to go through in the first one, I want you to identify what's the limit as x approaches 4 of f of x. And in the second one, I want you to find the limit as x approaches 5 of f of x. So take a minute, pause the video, take a minute to find those limits, and once you're done, come on back and we'll discuss what happened on these problems. Welcome back. In the first one, remember what's happening in this case. We want to know we want to find the limit as x approaches 4 of f of x. So as I come from the left, moving closer to 4, as I use x values getting closer and closer to 4, my function values are getting closer to 7. And as I come from the right, my function values are also getting closer to 7. So in this particular problem, I know the limit as x approaches 4 of f of x is going to be 7. In our second problem, notice what we have here. We have at 5, I know f of 5. When I plug 5 into f of x, I'm going to get the value 2. But the rest of the time, I'm going to be along this curve. So as x, we want to find the limit as x approaches 5. Well, as x approaches 5, again, but not equal to 5. As x approaches 5, I am on this portion of the curve. And as x moves closer and closer to 5, my y values are getting closer to 1. As I come from the right, as x moves closer and closer to 5, my y values end up getting closer and closer to 1 as well. So in this particular problem, I know the limit as x approaches 5 of f of x is going to be 1. At this point in time, you're probably wondering, when does a limit not exist? Well, there are 3 situations where the limit is not going to exist. Because remember, it is the one number that I am getting closer and closer to, the one real number I'm getting closer and closer to as x approaches c, but it's not equal to c. So the situations that we have, the first one that we're going to look at is what's called a step discontinuity. What we're looking at here is this one, the limit exists for every value on this except for c. Because look what happens as I move closer and closer to c from the left and from the right. As I move closer and closer to c from the left, my function values are getting closer and closer to 3. As I move closer and closer to c from the right, my function values are getting closer and closer to 5. So in this particular problem, remember, since it's supposed to be the one number, because I am not moving closer and closer to one number, but actually 2 numbers, on this particular problem, I would say that the limit here, as x approaches c of f of x, does not exist. The next one we have is where we have a vertical asymptote. And you're going to see 2 graphs here, and because they illustrate the 2 different situations you have, okay, in terms of vertical asymptote, where either as you come from the left and from the right towards the vertical asymptote, you are either going in the same direction or different directions. In both cases, though, what you have to keep in mind is that the limit does not exist in either one of these. A lot of people look at the first one, this one here, and they say, well, clearly, on this one, they say clearly the limit doesn't exist as x approaches c, because as I go in this direction here, as I come from the left, I'm going way, way up. I'm going up without bound. As I approach c from the right, I'm going down without bound. So you look at this, as I'm going in this direction, I'm going towards a positive infinity. In this direction, I'm going towards a negative infinity. So yes, they would sit there and say that the limit in this case does not exist because we are going off in different directions. But in the second one here, this one also, the limit does not exist. And it really comes from because of what a vertical asymptote is. What's going on when you have a vertical asymptote? As you approach a vertical asymptote, the rate of change of the function values for very small values of rates of change for x, the function values are changing a large amount. So what's happening is that the function values are growing without bound, and that's the key. So since I'm going from the left, I'm going in this direction, and I'm going up here. I'm going to be going up, growing without bound as I move closer and closer to c from the left, and as I move closer and closer to c from the right, I am also growing without bound. So in that case, the limit does not exist as well, because it is unbounded growth. I keep getting bigger and bigger and bigger. I'm not approaching one specific number. I keep getting much bigger with a very small change in x. So both of these here, the limit does not exist. Now, so you could go through for each of these, you could also write this. Now, this one right here, I have seen some people say, well, in this one, they would look at it and say, well, the limit then, as x approaches c of f of x, would be infinity. And that actually is acceptable, because infinity means that there is no limit. It doesn't exist there. Now, you got to keep in mind, though, this works for this one here. This works for this one here, but it doesn't work for the others. Okay? Where saying it does not exist works for all three. The other one we have is oscillating behavior. In oscillating behavior, what happens is it means that as I move closer and closer to C, my function values just are bouncing back and forth between two numbers faster and faster and faster. Often, if you look at a situation where you have oscillating behavior, as you move where C is, it will graphically, especially if you're doing a calculator, it's going to look like a big, thick bar. It's like a bar. For example, one of the examples in your book, it's on page 51. It's example number 5. It's looking at the limit as x approaches 0 of the sine of 1 over x. Now, it's important for you to recognize what's happening. As x moves closer and closer to 0, 1 over x is going to be getting bigger and bigger and bigger, or going in the negative direction as well. And what's going on there, because it's getting so big, the sine of 1 over x is going to be bouncing between 1 and -1 very, very quickly. It's not going to be that nice even curve that we graphed last year. It's going to be very, very fast. In fact, if you take a look at the graph on page 51 in your book, you will see that dark, thick, almost thick bar right at 0. And that's what's going to happen when we have oscillating behavior. And in that case right there, we would also say that this limit here does not exist. Now let's take a look at the formal definition of a limit. This is the definition that we will always come back to when we're trying to go and define things based on the limit process. Okay, so in this case, what we're going to do is we're going to let f be a function defined on an open interval containing c, except possibly at c itself. And we're going to let L, that's an L, be a real number. The statement, the limit as x approaches c of f of x equals L, means that for each number epsilon, that's a little backward, like a little e thing, epsilon greater than 0, there exists a number delta greater than 0, such that if the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. Let me say that again. We're going to let f be a function defined on an open interval containing c, except possibly at c itself. And we're going to let L be a real number. The statement, the limit as x approaches f of x of L, means that for each number epsilon greater than 0, there exists a number delta greater than 0, such that if the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. Take a minute right now, make sure you have this copied down, and when we go forward, we will see a diagram to kind of illustrate what this means. Here's a diagram that we can use to illustrate the formal definition of a limit that we just saw in the last slide. It might be helpful for you to go and at this point pause the video so you can copy this diagram into your notes right next to that definition that you just wrote, and then we'll go through the explanation in terms of how the definition works, is illustrated by this particular graph. So go ahead, pause the video, do that drawing, and then when you're ready, come on back. Okay, welcome back. Now, what's happening on this particular graph? We have a situation where I have a function y equals f of x, that is this function here, and I know that the limit of f of x as x approaches c is equal to L. In other words, as my x values get closer and closer to this value here, my function values are getting closer and closer to L. And I think you can look at that and can see that based on our discussions that we looked at graphically before. Now, what the definition says is that for every epsilon greater than 0, there exists a delta. Well, actually, for every epsilon greater than 0, there exist many deltas. But all you need to do is find one. For every epsilon greater than 0, there exists a delta such that if we are within delta, if we use a number within delta units of c, I will get a function value within epsilon units of L. So here's L. I have epsilon. I have moved epsilon units above and below L. So I have L plus epsilon here and L minus epsilon right here. So I've gone through. Now you got to think of that. That generally is going to be a very small number, but it's I've made it a little bit bigger here. And what happens is that I know that if that limit exists, if I move go pick a number within delta units of c. So I've gone through and just estimated a delta. So I went over delta units from c. I got here's c minus delta and here's c plus delta. And what happens, what this limit definition says, that if I use any values, if I plug any values between these two, between c minus delta and c plus delta, if I plug any of those values except for c itself, because remember the limit is looking at what happens as x approaches c but not equal to c, I will go and get a function value that falls in this between L plus epsilon and L minus epsilon. Now in this case, because of the delta I have, I actually have my function values falling closer to that. They're going to fall within these two. But it just illustrates the idea that for each epsilon there's many deltas. In this case, this delta works, but I could actually go a little bit bigger. Now let's take a look at an example of a problem in terms of finding the delta that we need to work with in this case. So in this case, what I have is a problem. I want to find I know that I'm being given that the limit as x approaches 2 of 4x minus 7 equals 1. I want to find delta for epsilon equal 2.1. Now I want to find a value of delta that can work. Now here's the thing you have to keep in mind. I know by the definition that the absolute value of f of x minus L is less than epsilon, and I know the absolute value of x minus c is going to be less than delta. Well, for this particular problem, c is 2. So I know that what I'm going to be looking at for this one is I want to look at the absolute value of x minus 2, and I want to find a number that I can plug in for delta to make this true. So now, what I know on this problem, I know f of x is 4x minus 7, and I know L is 1. So the absolute value, and I know epsilon is 0.1. So I know that we're going to get the absolute value of 4x minus 7 minus L, which is 1, is going to be less than 0.1, which was epsilon. Simplifying that, I get the absolute value of 4x minus 8 is less than 0.1. Now remember, I want to go and see if I want to transform this so I get x minus 2. Well, in this case, I can pull out a 4, so I get the absolute value of 4 times x minus 2 is less than 0.1. And I can also pull that out, so it'd be 4 times the absolute value of x minus 2 is less than 0.1. And then solving for that, I get that the absolute value of x minus 2 is less than 0.1 divided by 4, which 0.1 is 1/10. So when I simplify that, 0.1 over 4 is 1 over 40. So for this particular problem, when epsilon is 0.1, I can use delta equal to 1 over 40 to go through and say that, okay, that limit does exist. So with that, this does conclude the video dealing with some of the issues in terms of the finding the limit and the formal definition. Make sure, again, if you have any questions that you note those for me in your notes using a red pen. And then with that, I will see you in class.